Today we're going to talk about domains. So our objective today is that the students will determine the domain of various functions. So let's define domain and range. The domain is basically, when you talk about functions, it's the inputs, it's the x values, it's the independent variable. Okay, those are all different ways to describe the domain. So the range is the opposite of that. That's going to be the outputs. That's going to be the y values and the dependent variables. So the domain controls the range. A lot of times we can find the domain algebraically. With the range, quite often we have to look at it graphically to make sure we have the full range if we're defining a range. All right, so when we are defining domains, we tend to either use set notation or interval notation. So just a quick reminder, especially for set notation, that looks like this with the fancy braces, x such that blah, 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 and your domain would be right in there, like x is greater than 1 or x is not equal to 0 or whatever. Interval notation represents the same information, but you're using square brackets, rounded brackets. Both of those are used to define domains. All right, so we'll start with what we call explicit domains. Explicit domains are the ones that are already defined for you, so they are out there. You can see it. You don't have to do anything because we tell you what the domain is. I'm having trouble writing, sorry. They're already defined for you. So as an example, if we have f of x is equal to x squared, and then right next to it it says 0 is less than or equal to x, which is less than or equal to 5. Well, there's your domain. It's already defined. We only want values between 0 and 5 inclusive. So if I want to write the domain, I can just say, well, here's my domain, 0, 5, square bracket, square bracket. That is an explicit domain. So what we'll spend most of our time on are domains that are not explicit, where we have to find the domain or solve algebraically to find it. So when we're finding and defining a domain, we're basically stating where the function is defined. So that's kind of our goal. We want to represent the interval where my x values will work. So let's start with a polynomial function. F of x is equal to 2x squared plus 3x plus 1. A lot of times students will try to factor it and say that's the domain, but you don't have to. If you think about the function and what this graph looks like, there is no place in here, there is no value of x that will mess up this function. Basically, I can substitute any number I want, and this will generate an answer for me. So the domain in this case is going to be the set of all reals. We can write the fancy R. That stands for the set of all reals. So in the future, you can just write the fancy R. If you want to write it in interval notation, it's negative infinity to positive infinity. Okay? So that's when a function is defined everywhere. The second case is a rational function where I have a variable in the denominator. So we know this function is undefined when the denominator is equal to 0. So my restriction is this: the denominator cannot equal 0. So when I'm finding this domain, I got to say, well, x minus 4 cannot be equal to 0. So x cannot be equal to 4. 4 is the only number that isn't going to work here. So in set builder notation, you would say x such that x is not equal to 4. In interval notation, it would look like this: negative infinity up to 4 exclusive, 4 to infinity. When we have a radical expression, we are working with the real number plane, not the imaginary. So in this case, it's undefined when x is less than 0. So whatever we have for the radicand, which again is the expression underneath the radical sign, it can't be negative. So what we're going to do here is the domain has to be greater than or equal to 0. So the domain, if I'm solving one of these, it's got to be greater than or equal to 0. So you take whatever radicand is under there, and you set it greater than or equal to 0. In this case, there's no solving because it's a really basic function here. Greater than or equal to 0, set builder notation, x such that x is greater than or equal to 0. In interval notation, square bracket at 0, going to infinity, rounded. And then we have the combination of the previous two. So in this case, the denominator cannot be 0 because it's a fraction. And the radicand cannot be negative. So we need both of these situations to be true. So for them both, that means we can't be 0 or negative. So here you'll set the radicand to just greater than 0, not greater than or equal to, and solve it just like you did before. So if I look at the x minus 2, that's my radicand. So x minus 2 is greater than 0. X has to be greater than 0. So set builder notation, x such that x is greater than 0. Interval notation, now we're rounded at 0 to infinity because again, your denominator, it's okay for the radicand to be equal to 0. Oh, and I didn't even solve that right. Let me back up. That needs to be 2. Let me fix that. X is greater than 2. X is greater than 2. Rounded at 2. So again, the radicand, it's okay if it were just the radicand, it would be okay for it to be 0, but since it's in the denominator, it can't be, so it has to be greater than 0. And those are the 4 basic cases that you will see. So if I do just a few more examples here to find the domain, I have f of x is equal to x squared minus 4. A lot of students will factor that and try to tell me that the domain is like not equal to positive 2 and negative 2, but please be careful. This is a polynomial function. It is defined everywhere. So in this case, my answer is the set of all reals. And then the second case here, I have an explicit domain, so it's there, it's defined between 0 and 2 inclusive. So if I were to write my domain in interval notation, it would be 0, 2, both with the square brackets. Finally, I'll do one of these because there are multiple places where the function would be undefined. I don't care what the numerator is. In the denominator, I'm going to take the denominator and say, well, for the domain, x squared plus 9x plus 18 cannot be equal to 0. In this case, I have to factor and solve. X plus 3, x plus 6 cannot be equal to 0, so I have 2 points. X cannot be equal to negative 3. X cannot be equal to 6. In set builder notation, it would be x such that x is not equal to 3, negative 3. Well, let me erase that and fix it. Okay. X is not equal to negative 3. X is not equal to 6. In interval notation, it would be negative infinity up to negative 3, union negative 3 to 6, union 6 to infinity. Everything rounded because you cannot include that point. So that's a very basic introduction to finding the domains of various functions.